Hi, thanks. Thanks for giving me this chance to introduce our software and our work. So I will start my talk. So the name Yao comes from the first character of the unitary in Chinese. Yao is a software aims to help researchers design quantum algorithm in an efficient, generic, and extensible way in the cutting-edge Julia programming language. So first, I'd like to introduce other Yao ecosystem developers. So these are the core developers currently in the ecosystem. Before I go ahead, to give everyone a bit of context, what is Julia language? So Julia is a high-level programming language designed by Jeff, Stefan, Vera, and Alan. It looks like Python, but run as fast as C. The Julia community is very scientific computing centric. Yao is built along with many other scientific computing packages as well. So I stole this slide from Steven Johnson, who is the author of FFTW, which many of you might already know. He's also a main contributor to the Julia community. So to talk about Yao, I'll start with variational quantum algorithms, because initially Yao is designed for variational quantum algorithms, where we have a parameterized quantum circuit and a classical computer that optimize the circuit. But we later grow the ecosystem around it by introducing some more features. So as you can see in this review paper, Yao is one of the three frameworks that supports variational quantum algorithms. The core functionality of Yao is built around an intermediate representation called the quantum block intermediate representation. The idea of quantum block intermediate representation is quite simple. So here's an example how a quantum Fourier transformation is represented in this representation. So here on the left is quantum Fourier transformation circuit. Because it is recursive, we basically use some extra composite blocks, the red ones and the blue ones, to represent this circuit as a tree, so that we can represent and analysis this in a computer program. Based on this representation, Yao has a built-in automatic differentiation engine that make use of the reversibility of the quantum programs. So this gives us the ability to differentiate a simulation program efficiently without allocating too much extra memory. So here's actually I was in QHack 2019, which is 2 years ago. We simulate this AD engine allows us to simulate a 1,000 layer variational quantum circuit efficiently in simulation back in 2019, and we so that we can do something called pruning on this variational quantum circuit parameters. Back then, our team was called Day Strippers. So here's an overview of the whole Yao ecosystem. The whole Yao ecosystem is built around an intermediate representation that represents quantum circuit as a block, which is here. And then we build symbolic calculation, automatic differentiation on top of this representation. And we also use other packages in this ecosystem. For example, there's another large ecosystem around differential equation Julia. That also powers a lot of our simulations. And there's also Flux and Zygote provides classical automatic differentiation for neural networks and general classical programs. And there's Julia Statics and symbolic calculation using Sim engine. So there's a lot of code will just work if you combine other Julia packages with YAO, because the simulation and the backend are written as a generic program, which means it works on arbitrary types. So here is a benchmark of our generic quantum circuit simulator. As you can see, we achieve one of the best performance among other open source quantum circuit simulators. And the GPU part only takes about 300 lines of code. So it's powered by Julia's GPU compiler extension, which is very easy to use. As I mentioned, our quantum circuit simulator is a generic simulator, so which means it doesn't only work on normal floating points, it also works on arbitrary other types. For example, if you plug in some symbolic type, you can automatically gain the ability to do symbolic calculation. And if you plug in, for example, tropical number, then you'll be able to contract a tropical tensor network using our simulator. So this paper demonstrates how you'd actually do that. Last year we started working on our new compiler. Since we are still not satisfied with our current representation of using quantum blocks, and as part of the compiler development work, we start supporting using ZAX calculus to do quantum circuit optimization. So what is ZAX calculus? ZAX calculus is basically a special type of tensor network. It represents the tensors on Z and X basis as a diagram, so that using this diagram, we can analyze the Clifford component of your circuit and then remove this component, so that in the end, we can create a simplified circuit and let you run it faster. This is a Google Summer of Code project. There's also some research around this YAO ecosystem, and here's some research papers and citing YAO if you're interested to read about. So what I have just talked about are some already existing features in the Julia in the YAO ecosystem that is more mature and is released. And if you follow some Julia news, there is going to be a next big release, which is Julia 1.6. And for the coming Julia 1.6, there are a lot of compiler improvements in Julia, such as much better experience in just-in-time compilation latency, and the new abstract interpretation mechanism, and many more. So we're also developing some new exciting things that make use of the new features in Julia 1.6. So the first thing is a new simulator, but it's not a simulator, it's a meta simulator. So what is meta simulator? It's a tiny domain-specific language that generates a simulator directly. So as many of you might know, basically how to simulate a quantum circuit is about how to do matrix multiplication, or more generally, how to do spatial tensor contractions. So this involves one to find an optimal CPU or GPU kernel directly from your gates. So write this meta simulator that generates the kernel from a tiny kernel domain-specific language. And you can define your new simulator routine simply using one line, like this. And this results to up to 60 times speed up comparing to our current simulator. And of course, it still supports generic typing, which means if you plug in a symbolic type or tropical number type or even Grassmann number type, it will still work. Yeah, so that means this will allows you to not only use it for quantum circuits, but you can also use it for tensor networks. The next thing is our new domain-specific language, the YALAN. YALAN is designed to make use of Julia semantic as much as possible, so you don't have to care about any concept of blocks we currently have, and it supports Julia's multi-step dispatch. That means you can write high-level abstractions over your quantum or your classical quantum hyperprogram. So this gives you a much simpler way to define quantum programs. It is compatible with OpenQASM, which means you can import any legit OpenQASM program into Julia using YALAN, and then call your OpenQASM function from Julia and use the functions defined in OpenQASM combined with a Julia function. So here's a picture, and this is our OpenQASM front end. Here is the generic quantum routine defined by YALAN, and here is YAL compiler OpenQASM target. This is a project supported by UniFrance Small Grant 2020. So here, so now I will show a little bit about what this looks like. So basically, there's a new macro called device. This allows you to define a quantum function where we see it's a quantum routine, and you can use these annotations to define a circuit or a hybrid program. And if you happen to define as a pure quantum program, the compiler can automatically detect it by analyzing your program. So then we will be able to convert it to, for example, OpenQASM within QHack. And we can also turn on optimization. But here, because this task program is too simple, optimization does nothing. So now I'll run OpenQASM code. So you can use this new string literal to write or include other OpenQASM programs. So here's an example. We manually define a custom gate routine in OpenQASM, and then we include IBM's standard library. So this creates, as you can see, it creates a post. And it creates other gates like control X, which is defined in the standard library. And now we can just call these functions. So control X has two positions, and post. Oh, actually, I can measure on the first position, and then return the memory result. So as you can see, any compatible, so you can still have a little bit control flow if it's compatible with OpenCasm, but if you happen to write some non-compatible program, the compiler will error and tell you this is not compatible. So now we can turn on the optimization, and it will inline the program. It will inline the all the user-defined routines and apply Zest calculus on it. So this is still too simple for the Zest calculus path to simplify. But you can find more complicated programs in our examples. Okay, so this is the next coming new DSL for the YAO ecosystem, and it aims to design for hybrid program, not just the quantum programs. So that means you can also define just a normal function that has a classical parameter or whatever other Julia objects you want to insert it. The only thing is this is not compatible with OpenCasm anymore, so that you can't compile it to OpenCasm, but you can still do simulation on it. This will create a routine spec, and then you can apply treat that as a normal operator and apply to your register. Okay, so what is behind the scene? In general, a hybrid program is a program that contains classical operation and quantum operation that defines in a high-level programming language. So then the compiler will optimize and compile the program to a target. And if the target machine does support hybrid program, we can forward the program to a code generator, so we generate low-level hybrid instructions. If the target machine doesn't support a hybrid program, then we can partially evaluate this classical part, which means we execute the classical part on a classical machine and then forward pure quantum instructions to the target machine. The YAO compiler is an implementation of this kind of hybrid program compilation. So it is designed for it's designed as a compiler extension for Julia language instead of creating an entire new one. This means we insert several compiler extensions for the Julia compiler, which is only possible in Julia 1.6. And first, we insert a macro here, and we insert our own analysis path on Julia SSE-IR. SSE here stands for static single assignment. Then we use abstract interpretation mechanism to figure out which part is a quantum program, which part is not, and how to simplify this hybrid program. So then we, after we figure out different regions, we forward different regions to different optimizers. And then in the end, we combine them together back to the YAO-IR and forward them to the code generator, which can be OpenCasm or IBM's QObject or Bracket JQCD or our own emulator. So there are also some other coming features. For example, a new IBM client. So I can show you a little bit here. We can try to run a simple program here. Okay, and so we can use IBM's device, and you can select which device you want to use. So to save some
time and energy, I would just pick the IBM OpenCosm simulator here. All right. I need to have some return value. Okay, so this creates job info. So as you can see here, it's still validating. I think it's now it's complete. So this is a very quick demo of how this IBM client backend looks like. Okay, so yeah, that's most of my content of the content of my talk. And if you're interested in our software, you can check out our website and join and contribute to us and power your own research. Thanks, everyone.
Thank you so much, Roger. Lots of arguments already about what base indexing things should be happening in, I'm seeing in the chat. But really wanted to ask you a pretty fundamental question, which is why Julia? As somebody that's been Julia curious for pretty much since the language launched, what made you go down this route instead of picking the more traditional way of doing it in Python?
Right. So I was actually a PyTorch developer roughly about 3 or 4 years ago. And back then, Julia was in 1.0, and I was still working. I was still contributing code to PyTorch, trying to get a complex number to work, and using PyTorch to write some neural network answers. But then during the when I tried to fix the complex number problem, I realized almost every Python package have to implement their own tiny compiler.
So yeah, so the users are happy because they don't need to learn. It seems they don't need to learn a new language, but the developers are not so happy because they have to, burn a lot of brain time to implement a new compiler, which is not simple. So I was actually just chatting with some Amazon Bracket developers. So they want to develop a new compiler for Bracket, and it has to be Python because most people use Python. You gotta make like everyone happy who ever use your product. But however, if you want to build a new compiler in Python, you actually have to build an entire new language beneath that. The language takes a subset of the semantics of the Python programming language, which is basically just reinventing the wheels that Julia had already invented. So yeah, so that's basically why the general reason I moved to Julia about 3 or 4 years ago. And that's also because back in 2018, Julia is going to announce its 1.0. So I was thinking, okay, it's probably the right time to move. Because my first attempt to use Julia was actually back in 2015. So at that time, Julia is only 0.3. And I know the two chain are so terrible. It's much terrible than whatever it had in 2018. And the startup takes almost like a few seconds to start its REPL in 0.3. But now, so at that time, I tried it and I actually gave up. I moved back to using PyTorch. But now I think it's probably the right time. And I believe in general from technical aspect, designing a language for just-in-time compiler is the right path to solve the compilation problems. So no matter
people like the one index convention or not, there will be other language use the same method in the future, I'm pretty sure. So even Julia, maybe people abandoned it 10 years later, there definitely will be another language use the exactly same technique to solve the two language problem.
Yeah, I mean, it's really interesting. To me, the two language problem has never really been a problem. I've actually liked the flexibility of having the low level optimization to go after. But definitely there's a lot of things that are done right. Like I like the idea of a language which was not organically grown, but grown with a very specific idea and mission in mind. Can you comment on the quantum ecosystem in terms of the tool chains to support quantum research? In Julia, I think a lot of people here know what exists in Python, but I think there's far less that have a good grasp on what's happening in the Julia language.
Yeah, so there are actually quite a lot of effort on quantum physics, and we actually had a quantum physics BOF section in last Julia conference. So in general, besides the YAO ecosystem that focus on quantum circuit, there are also individual developers writing more simulation code package for more specific field, like more theoretical quantum information or quantum optics. And there are also experimentalists you make use of Julia's tap system to help them do the unit conversion. Besides that, because Julia have a very, well, I would say it's probably the best ecosystem currently you can get for differential equations. So there's a lot of experimental people around this ecosystem using differential equation solvers to solve their problem. And there are also Mouse working on iTensor. So some people might heard about him. So he was working on C++, like pure C++, and they moved to Julia. I think start from 2 years ago. And they also developed a bunch of tensor network tools. So I'm not a chemistry guy, but also I saw some people working on, for example, rewriting a DFT solver. So I'm not sure if that is better than WASP, but I mean there's these efforts. So and also molecular dynamics. So almost every field you can think about in quantum physics, there's someone working about it in Julia language.
That's really awesome. It seems like the ecosystem has grown quite a bit in general since last time I looked at it. For those of us that are sitting in the quantum computing space and are, I'm going to say, Julia curious, what would you say that right access point is? How would you suggest people actually get involved? And I'm sorry in advance for making you the Julia ambassador for all quantum computing people, but that's not what you've become. So tell us, how should we get involved? Where should we look for resources, and how should we get started?
So I would say from my own experience, getting started with Julia is very easy because it roughly looks like Python. But once you start using it, you find there are some differences. So the major difference, like when I started learning Julia, was actually the multiple dispatch. So as many people might be aware of, Julia doesn't have object-oriented or class-based object-oriented programming. So what we use in Julia is a polymorphism based on multiple dispatch. It's a mechanism in between pure functional programming and object-oriented programming. So I would say if you want to master programming in Julia, that's probably the first thing to understand. There is a very nice talk by Stefan in 2019 Julia.com, which the title is The Unreasonable Efficiency of Multiple Dispatch. So actually, there one piece of the slide, which are the tropical number
tensor network is basically impossible in any Python packages, simply because there's two languages and there's only simple dispatch, so that you can't implement a generic typed simulator that supports tropical network. So if you want to support that, that means you have to write a completely new simulator in C++ and bind that to Python. So that's going to be a lot more work.
Yep. I'm not going to spoil any surprises, but that definitely sounds very familiar. That's great to hear. So you did demo the IBM backend that can connect to YAO. Are there any other backends that you currently support?
So we're also working on Bracket backend. So these Bracket and IBM are the current. Well, they're actually still work in progress. So I haven't released a version for the Bracket, but there is one release version for the IBM. And these are the only two backend for Harvard for now. Yes.
So as somebody who may be shifting away a little bit from the Julia and YAO specific questions, as someone who's gone through a QHack before, granted it was a very different one. It was in the before days when we were able to get together in our downtown office. But what suggestion would you make to the people that are now going to enter this open hackathon portion about the type of projects that they should be looking at or tackling?
So I would say back then we came out with the idea with after quite a few discussions, and it was so I guess the key point is enjoy the hackathon time, and somehow some idea will automatically came out of your mind. And if you happen to find someone else that is interested in the same idea, and then you can start to work together.
What do you think of the hackathon project of porting all of Penny Lane to Julia? You think that's a great idea?
Yeah, but I doubt. I mean, there's a lot of some tutorials and detailed features already written in Penny Lane, so I doubt the times how much time you need to port it to Julia. But I definitely support this idea.
That's awesome. There's a question that says basically it just reads, I didn't quite get it. What is YAOLang compiled to? YAO.jl? So maybe if you could just go over the breakdown of the domain-specific language versus the package.
Oh yeah, so YAOLang doesn't compile to YAO.jl. So modern compilers have multiple compile stage. So that means you compile to different things during the compilation, and it also depends on your compile target. So for example, you can compile C++ to an ARM CPU or an FPGA or a GPU. It depends on which target you choose. It's the same for YAOLang. You can choose to compile it to IBM's QObject or OpenChasm, or we're also developing a new MLIR-based format IR that can further lower things to FPGAs. That eventually will be the controller in a experiment. So it kind of depends on the context and what compiler options you pick. But the long-term goal on our side is to make the whole pipeline work.
Awesome. First of all, there's a lot of love for you out there, both in terms of the research direction as well as being brave enough to do a live coding demo. There is one question here that says, basically tackling the two-language problem in Python. You mentioned that as being one of the good reasons to move over to Julia, but they're asking, have you tried JAX before? Nearly everything except the XLA stuff you can do with JAX.
Yeah, actually, JAX people, so some of the JAX core developer has very close connection to Julia community.
So JAX is more like workaround to this problem, and it's actually a very good workaround, I would say, because I think most compiler people would agree that the solution to Python just-in-time compiler in general, the generic just-in-time compiler, is just very hard, and it kind of fails after the 2012 blog post from the Python developer. So JAX, I think JAX is a very good workaround because it focuses on the machine learning field. So it's just a very useful subset of the Python language to support, so that it fulfills most of the use cases, and you don't feel it's actually a subset. But still it's actually a subset. Yeah, so XLA and HLO actually, this effort on JAX later also came into the MLIR, which the full name is multi-level IR. So the Julia folks are also porting part of the Julia compiler into MLIR, which is called the Brutus project. Our new Yao compiler is also part of this. So I will see like there's no actual barrier between all these different solutions. Like the compiler people just want to solve the problem. And I would say currently, if you just want to do neural networks, you want to do like deep learning, JAX is a better choice currently than Julia. It's simply because JAX is much more mature. Yeah, but from the technical point, I would see like the Julia solution is still better because it doesn't have the historical burden.
Awesome. So what I'm hearing here is you're going to have a weekly session on Twitch under the QHack channel, teaching all us quantum people how to program in Julia, so you could get us all off of the terrible language that Python is. Is that right, Roger?
Yeah, that's yeah.
Awesome. Moving on to maybe something completely separate from the technical stuff. To tell me a little bit more about your Dota hobby. Is this something that you've actually done more competitively, or is it completely on the amateur level right now?
Well, it's hard to say because I never actually tried to make myself a super competitive player in Dota. But I've been start playing Dota since I was undergrad. It's like, it's like your Friday afternoon beer. I played it at work.
Yeah, we at Xanadu, when we first moved into lockdown, we actually ended up doing a lot of Team Fortress 2, as it was the only game that was completely cross-platform. It didn't matter what you had, you'd be able to run it. So Friday nights at 8:30, it was pretty regular at the beginning of the lockdown. We also have some pretty competitive Smash players, but I don't think there's anyone that plays Dota. I'm not sure. I'm looking at the chat right now to see if anyone comes up. But if we find someone, we might also have to do a live stream of a Dota competition between Yao and Penny Lane to see which one comes up on top.
Nice. Yeah, we could do that.
I'm currently looking for challenges in either the video game realm or table tennis is another thing we're obsessively competitive about at Xanadu. So if you want to put a team together, send them our way as well.
Yeah, I also missed the video game bar event in last QHack.
You were too busy working. Yeah. So our last QHack was themed not with synthwave like this one, but with good old-fashioned 8-bit video games. So we brought in a whole bunch of emulation stations, thinking that people would have a great time and relax and play, but everybody just worked all the way through. So we'll have to have people back to enjoy more of the atmosphere. Awesome. Roger, thank you so much. It's been great. I do want to do one more thing before you go. At the beginning of when we started announcing the QHack event, we actually made a call for general memes around quantum computing and quantum machine learning. We got a whole bunch of submissions. We're going to judge them today at the end of the day. But we also have a whole bunch that we can't judge because they came from people from Xanadu or friends or family. So it wouldn't be appropriate for them to win. So just want to get your thoughts on a couple of them. We're going to take a look. They're all going to be, again, QML themed. We'll see what Paul pulls up here for us. I have no idea what's going to come up, so I can't say if it's going to be good or bad. This is a pretty classic format, I would say. How do you feel about this? This is definitely my approach to quantum machine learning. It's much easier, much more enjoyable to just take the Penny Lane tutorial notebook and go with it. I feel you feel underwhelmed, Roger. I feel this person could have done better.
Yeah, this reminds me of some guy's Twitter. I forget. Basically, it was seeing he can implement like something using NumPy directly. Well, actually, I also have some blog posts teaching you how to implement a top performance emulator in one day.
Nice. You'll definitely have to share with the channel. Let's do one more. Paul, let's throw up the next one. This one I love. This one I lost my mind on first time I got to see it. I feel it's such a classic. It doesn't matter what you put down at the bottom. It's going to be funny with this guy. You could take any quantum phrase and smash it on the bottom, and I think it works.
Yeah, this one looks cool.
All right, one more, Paul. I think I know which one might be coming up next. I'm starting to remember. This is classic. I'm going to say this is probably our head of software, Nathan Kaloran, throwing this one up. But I do like the dignity of the term quantum differentiable programming as opposed to the problematic quantum machine learning. What are your thoughts on the distinction and how we should classify this whole approach to quantum computing?
Yeah, I also support the phrase quantum differentiable programming. Like differentiable programming is kind of part of the future direction of softwares as well. Awesome. Thank you so much, Roger. Definitely don't be a stranger. Drop by once you're allowed to again. We're not that far away. And thanks again for giving your wonderful talk. Sure. See ya.